Yes, sir.
Okay. Thirumagal ma'am, are you ready?
Yes, sir.
Okay. Thank you, ma'am. Very good morning, one and all gathered here. On behalf of King's College of Engineering, we welcome you all for the Alumni Series webinar, Day 5. Today's resource person, Mr. P. Aravind Preshant. He is a software engineer from Apple, California, USA. I request Mrs. P. Thirumagal, Assistant Professor for EC Department, to deliver welcome address and introduction to Chief Guest. Please, ma'am.
Very pleasant morning to one and all present here. I would like to welcome you all for the fifth day of this alumni series webinar on robotics, organized by King's College of Engineering, jointly organized by Department of Electronics and Communication Engineering. On behalf of our management, principal, HOD, staff members, and students, I would like to express my warm welcome to our alumni, Mr. P. Aravind Prashant, and all our participants. I take this opportunity and I am very proud to introduce our alumni and today's resource person, Mr. P. Aravind Prashant, software engineer at Apple, California, USA. He completed his BA degree from King's College of Engineering in the year of 2012 and master degree from Regina Institute of Technology, USA. He has over 8 years of experience in field of software by starting as a project intern in CAIR and now as a software engineer in Apple, California, USA. He has been part of 4 different important projects such as brilliant, attentive, encouraging personality is present among us. Hope we will learn something new from this section. Please join the section. Thank you, sir.
Aravind?
Uh,
Carry
Thank you
on.
so much, Thirumagal ma'am. Thank you so much for the kind words. First of all, I'd really like to thank the department, principal ma'am, HOD ma'am, and Rajbirian sir for organizing this and giving me this opportunity to present this topic in front of you. As this topic is, I feel, in my opinion, is very interesting. So I hope that by the end of the presentation, at least some of you, if not all of you, have some generate like spark this presentation spark some interest in all of you. So I will, without further ado, I'll start the presentation. Yeah, I hope you can see my screen. Please let me know if not. Um,
Yes, your screen is visible. Carry on.
yeah. Okay. So yeah. So this session is going to be purely introductory. So it's not going to go into too much depth, too much depth into the topics that I'm going to present, but it's just going to be sort of an overview of some topics in robotics. Robotics is such a huge field that there is no way that I can cover all of it in one go and like in an hour session. So it's going to be most like it's going to give you a flavor of the different sort of sections of robotics. So yeah, sort of like this is the rough agenda. So just start with an introduction and like go over like what ROS is, an overview of simulators, sensors, perception, SLAM, planning algorithms, and reinforcement learning. And I'll end the presentation with sort of more technical details and like details about my master's thesis, um, which was exploration of an unknown environment using multiple robots. So yeah, introduction. Like before we get into the different like sort of sections or fields in robotics, I think it's important to understand like what is a robot. There are many definitions that one can come up with. So I'm picking some like one of the definitions that I feel is a good definition of what is a robot. So this is given by Professor Anka Dragan from UC Berkeley. She says that I would say that a robot is a physically embodied artificially intelligent agent that can take actions that have effects on the physical world. We can also test this definition. So if we think about our favorite robot, which is I think like from the movie Robo Chitty, then you can see that he is a physically embodied artificially intelligent agent, and he does take actions that do have effects on the physical world. So that checks out. But I say that as a joke, but you can think of other agents that you might think of as robots, like an autonomous drone, which basically without any human intervention can make decisions and get from point A to point B. Like right now, like there are companies like Amazon that are doing autonomous delivery of packages and stuff like that. So yeah, so which will again so I feel that this is a good enough, pretty good definition of what a robot is. So if you think of like just if you can't just say that it's a let's say an electronic instrument, because like if you compare it to like a fridge, then that's not a robot, obviously, because it doesn't make decisions on its own and stuff like that. So that's sort of like what I think of as is a robot. Now, if you think about the robot, there are like two main sort of parts. One is the actual hardware, the physical robot, and the other big part is the software. So the algorithms that run on the robot. So these are two big parts. So there needs to be some way of like communicating for between the software and the hardware. So that's where ROS comes in. ROS is a robot is the robot operating system. It's actually not an operating system, but it's sort of like a middleware, which basically acts as an interface between the software, which are the algorithms that need to run on the robot, and the hardware, the robotic hardware itself. So yeah, so that's ROS. It's very convenient because it provides a flexible framework for writing robot software. It has a lot of tools, libraries, and conventions that aim to simplify the task of creating these complex robots. The good thing about this is that you have a common platform where researchers and roboticists from around the world can contribute to this common framework, and people can focus on what they're good at or what they want to be good at, instead of trying to do everything by themselves. This saves a lot of time in research. For example, if you are a computer vision scientist and you just want to write algorithms that the computer vision algorithms, then you can focus on that, and then some other roboticists from some other part of the world can use that package to write their own algorithms which are on top of this, use the output from this particular from the computer vision algorithm. So what ROS, like sort of an overview of ROS, what ROS is basically, like I said, it's a middleware. The framework is as follows: the ROS master node. The ROS master is basically responsible for the ROS master is responsible for registration, managing names and registration services to the nodes within the ROS system, where each node is basically some piece of software which takes in a set of inputs and optionally publishes some set of outputs as well. So, for example, let's assume this is some computer vision algorithm, then this is some planning algorithm, then the computer vision algorithm's output can be published to a topic where the planning algorithm can subscribe to that topic and make decision on its own. So the node is the ROS master is responsible for facilitating this communication between the two nodes, basically. Yeah, so that's ROS. That's sort of like a very high level overview of what ROS is, and it's really easy to like start using. There are a bunch of really good tutorials on ROS as well. I've added a link there if anyone is interested in getting started with that. All you need is it's a Linux laptop, Or you can also probably use a Windows laptop and use a virtual machine and install Linux and use that. But like some of the stuff that I'm going to talk about later in the presentation, those are very like graphics intensive, and like this was back in 2015 when I used it, and that was not very feasible. So it may be possible with the hardware that we have right now. But yeah, the ROS framework works best with Linux. So if you have a Linux machine, and yeah, you're good to go. So the only prerequisite that you would need is knowledge of either C++ or Python. So one of these two languages, if you know one of these two languages, you can just get started with ROS and robotics in general, and you can start work like exploring the world, the robotics world. So ROS facilitates this like interface between software and hardware. Well, what if you don't have hardware? Or hardware is really expensive. So like the platform that I had used for my like master's thesis um, was provided by the university, and that was around $10,000. So it's like really expensive, and it's for any individual to buy that. It's probably not possible. So instead you can use simulators, which basically give you the ability to implement your algorithms and test them out without having to spend money on hardware. So there are two main simulators that people use in the robotics community. One is Gazebo, the other is MATLAB. MATLAB is a very useful tool. Like the robotic system toolbox has been improving quite a bit over the past few years, and they've improved a lot. And then it's very helpful for rapid prototyping, just testing out your algorithms. Yeah, it's very helpful. But on the other hand, Gazebo is a physics simulator where you can actually simulate the real world almost, and like you have packages for all the hardware, like most of the robots that you have in the market, sensors that you have in the market, and you can like really with high fidelity uh, recreate the world where you can test out your algorithm in Gazebo. So yeah, like I've added links to both of these if you are interested to look at them as well. Um, so yeah, so you really don't need to spend money on hardware to like a robotic system, excuse me, to get started with robotics. Um, yeah, so like all you need is a laptop with Linux installed. You can install ROS, you can install Gazebo, um, and you can get started with robotics. You can start implementing your algorithm. There's so many packages, ROS packages that you can make use of, and yeah, it's really easy to get started. And there are like if there's any questions regarding that, you can always ask me. Like I forgot to mention, but like throughout the presentation, if you have any questions, please just like note, if you can note down the slide number, you can go back and I can answer any questions you may have regarding this or any of the slides in the presentation. Um, yeah, so let's like sort of what are the different kind of sensors that are used in robotics. There are so many. I've just listed like some of the popular ones that people use. The basic, like really basic one is the cameras, where it's just a camera which takes in images and you can do processing on that. There's the LiDAR, which is light detection and light detection and ranging, which is basically a laser sensor that uses light waves to sense the environment. Basically, it uses ray casting, so it shoots more than like 150,000 pulses per second, and it receives it off obstacles, and that's how we know where the obstacles are in the environment. Sonar is similar; it uses sound waves instead, and radar is also similar to lidar, but it uses radio waves. So all these are used to detect obstacles in the environment. There are tactical sensors as well, which are basically used for like those human type robots where you need to touch them to understand what the object is. So those are tactile sensors where you could like the robot actually physically touches the object to understand what it is. There's accelerometer as well, and which and there are like a bunch of other sensors. These are just a few. In case you like are you have any interest in like building your own robotic platforms, and you get like some of them you do get some of these for cheap as well. So you can try it. Like obviously, like I said, if not, you can always go the simulator route. Um, okay, so yeah, so let's go to perception. What does perception mean? So like this is a transition from sensor. So perception is how do we sense the environment or perceive the environment. So so the sensors are telling you, okay, there's something here, but like you need to figure out what is there. So for the instance, if the camera is giving you images, it's just sending you images and it's not doing any, like it's not telling you what is there in the image. So perception is the field of sort of robotics where you try to understand what is there, what the sensor is telling you, what is the object in the sensor, and build a representation, like using that build a representation, internal representation of the environment. um, so number one is object detection, which is the process of classifying and determining an object's position in the image. So if you look at the first image, you can see that there's a car, like, but the camera doesn't tell us that there's a car. So we need to write our own algorithms to figure out that there's a car. And once you figure out that there is a car in the image, you also need to figure out where the car is in the image. So this two-step sort of process is called classification with localization. So now, like, this is for a single object. You can see there's one car. You're localizing that car here. This can also be extended to multiple objects as well. So like there you see here there are two cars. Yeah, so that's what so you like you have a algorithm to, so we have to write, this is where computer vision comes in, where you have to write an algorithm to detect a car in the image and then localize that or find the position of that image in the car. So position of the car in the image. Sorry about that. Yeah, so if you look at like these are two very famous like object detection frameworks. The Bialo-Jones object detection framework is very popular in face detection. So it is very good at detecting faces. And it's a machine learning framework. YOLO is it's funnily named YOLO. You only look once is a very recent paper. I think it was last year, where it's a deep learning framework where you only get one image and you detect and like you detect all the objects in the image, and it works for multiple objects in the image as well. And it's like it works really well. So yeah, so image classification is basically how good your input data is. So like if you have a face detection algorithm, then you need to train your model with like lots and lots of face images, and you need to have diversity in the images as well. Like you need like you need people of all different races, all different genders, all different ages, because if my image is fed to the system, then probably would not identify it. So training data is really important, and obviously the algorithm is important as well, but the training data is also really important for these kind of techniques. So yeah, now once you've detected the object in the image, we need to track it over time as well. So every time like detection is sort of expensive, so once we detect it, we need to track it over time as well. So that's where object tracking comes in. So once you have a measurement, you need to sort of make sure follow it in the image, see where it's moving. So one of the techniques that people use is the Kalman filter. Um, so Kalman filter uh, is a tracking technique. So for example, let's say this is a 1D problem here, one-dimensional problem here, but it can be extended to multiple dimensions as well. So the basic idea is you have some sort of motion model of the object with which you make a prediction, and then you get a measurement from the sensor saying, okay, this is where the object is, and then you use that information to get the object's actual position. So, for example, here you see it's a Gaussian. The this here we think that the object is here with a very high probability, and here with very low probability. The main thing to understand is that if this is wide, that means that we are not very certain where the object is, and if it's like thin and tall, that means we're quite certain where the object is. So like this, the thinner and taller the curve, the more certain we are of the object's position. So for in this 1D example, if we see, so this is where we predicted. So that's the red line here. We get a measurement here, and then we combine these two, and you see this blue curve here, which is the corrected measurement. So that means that if you combine two weak sort of predictions of where the object is, you get a way more confident estimate of where the object is. So this just keeps this step is repeated multiple times, and then you get a like after a few measurements, you get like you are very confident on where the object is. And yeah, obviously you need to weigh your inputs. So like whether you're giving your measurement more whether you're confident about your measurement more or the prediction more. So that's what it's a weighted mean. So it just combines those two. So depending on what you trust more, then you can adjust the gain, which is called the Kalman gain. And there are equations that you can look through. I'm not going to go through those because that might take a little more time. But I've added a link to the equations here, so for anyone who's interested in that. Yeah, so once you have that, you can there are many applications of it. So one of those is simultaneous localization and mapping. What that is that the robot is trying to build the map while trying to determine its own pose in the map. So it's like a two-headed problem where you don't know what the map looks like, and you don't know what your position is in the map. So that's what SLAM is. That's the SLAM problem. And like you see on the right here, this is some building, and this is the map that was built by some robot using I believe a laser sensor. So this is an occupancy grid representation of the map where what it means is that the white space that you see here all over here is free space. That means there's no obstacles. The black lines here are obstacles or walls, and the gray is unknown space. So with every measurement here that you get from the laser, you either decrease its so each cell has a probability of it being occupied. So if it's closer to 1, that means it's highly probable that it's an obstacle. If it's closer to 0, that means highly likely that it's free space, and 0.5 is basically unknown. So that's what SLAM is. I have added, so this is from the Open SLAM project, and it's also available as a package in ROS. So you don't need to know SLAM in order to, like, if you're trying to write some sort of like exploration algorithm, something like that, then you don't need to write your own SLAM algorithm that will take years. So if someone has already done it, then you can make use of this package and use it for your research. Yeah, like jumping on to planning algorithms now, I'm going to just give a brief overview of like sort of two quite popular algorithms. One is a discrete. When the world is discrete. The other is when the world is continuous. So the A-star algorithm is very popular. I'm sure like some of you might have already heard about it. That's a shortest path algorithm, which is basically if the red is your source and the green is your goal position, then you need to find a path in the grid that is the shortest path. So what you do is you have, let's say each grid cell is a vertex in the graph. You pick one which minimizes two things. So one is, so you pick with a minimum f, which is comprised of two things, g and h, where g is the movement cost to move from the starting point to the given square, and h is the estimated cost to movement cost from that square to the final destination. For example, let's say this one. Let's say in the starting position we have three options. We either go here, here, or here. From like so for here, this is the one where that function is minimized because the cost here, all of these are one, so that's fine. So if you have a sort of an estimate, we don't know how far, we have no idea how far the goal is from this position, but we have sort of like an estimate where we can just take the short like straight line distance, which is also called the Euclidean distance, which is sort of like an underestimate of how, like, you can't be when the distance cannot be lesser than the Euclidean distance or the straight line distance, right? So that's sort of like an underestimate of how much the distance is. So like if you compute the straight line distance from here, from here, from here, this one will be the minimum. So and that's the next rate that we choose, and then this process is repeated till you get to the goal. A star is complete. By that, what I mean by that is A star will, for a finite grid, A star will always find the path to a goal if path to the goal if one exists. If not, it will terminate and say that there's no path. So for example, if this cell here was also blocked, then there's no way that you can get from the source to goal, right? So A star will say that there is no path. So that's why A star is complete. And if the heuristic is a good heuristic, it's an underestimate, then A star will provide the optimal solution. That is the shortest path in the graph. Yeah. So this is for A star is for it's good. Like there are other shortest path algorithms as well in the grid, Dijkstra's breadth first search. But yeah, A star is one of the most popular ones, and like most people use A star. Most people use A star because it gives you the optimal solution. The heuristic is good and it's complete as well, and it's fast too. Like this is for a discrete environment, but not in all environments are discrete. So generally in the real world we work with in the continuous space. So the other like sort of path planning, very popular is the RRT, which is the rapidly exploring random trees algorithm. So what you do is we start at Q. This is the source. This is your goal. You start with some. Let's say we've somehow come to this, and this is our tree. We no. So this is not the goal. Sorry, there's a goal somewhere else, and then this is, let's say, an intermediate step where we have a tree. Now we sample a point somewhere in free space, and we try to go in that direction by epsilon. And if there is no obstacle and we can reach from this vertex, which is the nearest vertex to the Q new, without hitting an obstacle, then that means that we can grow the tree. So this works really well in practice. And like as you can see, the red squares are the obstacles, and like this is the starting point, this is the goal point. After some iterations, the RRT the graph reaches the goal. And like once you have this graph, then you can use some shortest path algorithm like A star to build the path here. So as you can see here, though, the path is not optimal. It takes a lot of unwanted turns, and it's not the optimal path to the goal. But there are other algorithms like RRT star, which is a variant of this algorithm, where the tree is rewired after every step to make sure that it's straight. And that algorithm I think it is probabilistically it gives you the optimal algorithm, optimal solution. There are multiple variants of RRT, and like a lot of people, this is very popular. And like I've added a link to how, if you want to understand it better. I've probably not done justice to this algorithm, like I have not explained it very clearly, but it's a really interesting algorithm to understand as well. The other thing is, so those are perception planning, and I know there was a session on machine learning a few days ago by another speaker. I'm not sure if this was excuse me, if reinforcement learning was covered in that session, but just for the benefit of people who didn't attend that session, and just to make sure if it wasn't covered, I want to just give a basic idea of what reinforcement learning is. So reinforcement learning is basically you have an agent and you have the environment where the agent at some time t takes an action a, so that's a of t, and it goes through some state transition, and you observe the state again, and you assign some reward to it. So the agent receives feedback in the form of rewards after every step, and the utility is defined by the reward function, and the aim of the algorithm is to come up with a policy that maximizes the expected reward. So you have to come up with a policy where you are trying to maximize the reward. The reward we have to define what the reward function is, and then you can then the algorithm so basically it learns how to maximize that reward. So just as an example, this is one of the projects that we had done for our computer. So my computer vision project at Virginia Tech. This is where Flappy Bird is trying to learn how to play the game by itself. So this is the reinforcement learning algorithm trying to learn how to do it by itself. So in the beginning, you can see it doesn't know that it shouldn't fall to the ground, and then you assign a huge negative reward for dying in this case, and then it learns that it shouldn't fall down and start jumping. So, and then it doesn't fall to the ground every time, and then it starts jumping. It hits the pipe because it doesn't know that it has to jump over the pipe. It keeps going, and then after a lot of tries, it finally learns that it needs to jump through these pipes all by itself. There's no human intervention involved in this, and it just learns by itself that it needs to jump through these pipes. And that's that was a fun project that we did for our computer vision class. So the other one is this is the DeepMind's project where they had tried to come up with agents that learn how to walk and sort of other dynamics. So this is all the stuff that you have. So this is the agent. This agent here is this agent here is trying to, on the right, is trying to learn how to walk. So it just falls on the ground, doesn't know how to walk. This you can look at other agents here as well. They're trying to do other things, but after some training, a lot of training actually, you see that this agent here on the right, bottom right, learns how to walk all by itself without any human intervention. So reinforcement learning is a really emerging, it's a everyone is working on, a lot of people are working on that right now, and it's a very exciting field to be in right now. Some of you, a lot of you might have heard about AlphaGo, which was an AI agent, which was basically a reinforcement learned agent that beat the the world champion of the game called Go. The Go is a very complicated game, and the AI agent basically learned how to beat the world champion at that. So that's pretty cool. So moving on from all that, so that was sort of all the there are many more fields or sections or fields in robotics. Machine learning, artificial intelligence is a huge field by itself as well. I'm sure you might have learned about it in the other session that was there. And you can learn a lot of things. I mean, it's the hot thing right now. Everyone is working on machine learning right now. So that's so there are other fields that probably I have definitely missed in robotics, like the controls part and stuff like that. That's not something that I've worked with, so I don't know if I can talk too much about that. But yeah, that's also a really interesting field. A lot of people are working on that too. So now, shifting gears, I'm going to go through sort of some details about my master's thesis that I did in Virginia Tech, which is basically exploration of an unknown environment using multiple robots. The motivation behind the thesis was that there are environments where humans can't, when it's not safe for humans to enter and perform the duty that needs to be performed. So, for example, there's an earthquake and there's just rubble all over, and it's very dangerous for a human to go and try and rescue people inside, because uh, like, what if a rubble falls and like that human, like one more human is trapped or more humans are trapped. So in that case, so if environments where it's unsuitable for humans, it makes sense to send robots to do that job. And yeah, instead of using one robot, it makes sense that you use multiple robots so that you can do it faster. So there are two approaches to the exploration problem. One is the information theoretic approach. One is the computational geometric approach. The information theoretic exploration, basically, the objective is to obtain accurate maps of the environment under an exploration. So this is sort of the occupancy grid that we saw earlier from the mapping. So this is white. So this is free space. This is where the robot is. This is this is unknown space, and this is a frontier. Basically, that's the boundary between free space and unknown space, because that's where you don't know what is there. So if the robot needs to move here and needs to sense again to see what's there. Geometry explorations are mostly sort of like perfect sensing cases where it's a pure algorithm. There's no uncertainty, there's no sensor noise, there's nothing like that, and it's just purely there to give global guarantees on a pure algorithmic level. So the motivation again. So there are two different approaches. The information theoretic approaches are usually they have some pros, that they take sensor models into account and they work in complex environments. But the con is that they're typically greedy. So there's no global guarantees on how long the algorithm is going to take. On the other hand, computational geometric approaches have global guarantees, but the con is that they assume perfect sensing, which is not true in the real world, and they take in simple environments, and they don't take into account any uncertainty in the environment as well. So the motivation was to combine these two, so yeah, the multi-robot exploration algorithm is what combines the geometric and information theoretic approaches together to get the best of both worlds. So the theoretical contribution was that it's a constant comparative ratio for orthogonal polygons. I'll go over that in a little bit. The experimental contribution was that we show how to adapt the algorithm to the real world, and we evaluate with simulations and experiments. I presented this paper at the workshop at Wafer 2016, and it's now a journal paper as well. I've added a link to my paper if anyone is interested in reading that. Yeah, it's a journal paper. So the assumption, so like I mentioned here, that this is under certain assumptions. So the assumption is that the environment is a 2D orthogonal polygon without any holes. Orthogonal polygon just means that the walls of the environment are either aligned with the x-axis or the y-axis. So it's like there's a 90-degree angle between every wall in the environment. The robots have omnidirectional sensing. That means that the robot has a 360 degrees field of view, and this is for the theoretical part of the contribution. So that's why we are making these assumptions. So the sensors have infinite sensing range. All robots start at the same location, and all robots have equal speed. So they are homogeneous in that sense. So they're all robots essentially are the same. So what we proved in the paper was that the comparative ratio of our algorithm was a constant factor for a given number of robots. So the formula that you see here was the comparative ratio. I'll go through what the comparative ratio is. Like basically, it's the cost of an online algorithm to the max cost of the online algorithm to the cost of the optimal offline algorithm. So the optimal offline algorithm knows the environment beforehand, and it knows what to do, and so that is the optimal. So that's the optimal offline algorithm. So that's the best you can do. There's no way any algorithm can do better than that. So if you have a comparative ratio of 1, that means that your algorithm is the optimal algorithm. But in the case of an online algorithm, we don't know the environment beforehand. So we have to do some exploration that turns out that it's some factor of this. And as long as it's a comparative, as long as that is a constant factor, it's the guarantee is good and the algorithm is good. So if you anyone who's in computer science would or like anyone who's worked on sort of like the analysis of algorithms, we say that if it's a constant factor of the optimal algorithm, the constant factor of the input, then it's a good algorithm. So it's sort of a similar idea here. So I have this problem which I really like because it like helps explain what a comparative ratio is. For example, let's say this is called the lost cow problem. So let's say there's a cow and there's a one-dimensional line. So the cow can either go left or either go right, and there's just a fence and there's a gate. So the cow doesn't know where the gate is. So it has to find out. If you tell the cow that it's, let's say it's 1 unit away from wherever you are, then in that case the cow, let's say, goes in the wrong direction first. So it goes 1 unit to the right. It's not the gate isn't there, so it goes 2 units to the left, and it finds that there's a gate. So in this case, the comparative ratio, if you know that it's only 1 unit away, it's 3, because the optimal algorithm would have known that the gate is to the left and would have gone to the left straight away instead of going in the wrong direction. Yeah, so that's the case where it's only 1 unit away. But let's say it's at least 1 unit away. What is the strategy to sort of like explore this 1D fence to find the gate? It turns out that the algorithm is it's called the doubling strategy, where you double the amount that you go in each direction every time. So let's say you go 1 unit to the left first, then next time you go 2 units from the origin to the left, to the right, and you just keep doubling, and then you'll eventually find the gate. And it turns out that this is the best online algorithm. I think this is, I mean, from what I know, this is the best online algorithm you can have. And it turns out that the competitive ratio of this algorithm is 9. So in no case you would be more than 9 times the optimal algorithm. And I've added a link in case you want to learn more about the algorithm itself or how they derive the competitive ratio. Okay, so I'm just going to give you an overview of the algorithm that we used. It's basically abstracting the environment as a tree that you see on the right. So the environment is on the left, like you see, it's an orthogonal polygon, so where like every wall is like 90 degrees to another wall. So the basic idea is that you abstract it as a tree. So the tree is that you see on the right, and if you sort of perform a breadth first search on the tree, that would mean that you've explored the environment itself as well. So this is why the no holes in the environment point was important, because if you have a graph, then it becomes cyclical and the guarantee doesn't hold anymore. So basically you have a team of robots, you build a tree from the starting position, which is A here. At A, you see 2 like blocking vertices, which means that that's where your visibility ends. You add 2 goals, B and C. You 2 more. Let's say there's a robot of the team of 4 robots. 2 move to the right, 2 move to the left, and and you build a tree. And once you've explored the tree, that means that you explored the environment as well. So that was basically the idea behind the algorithm. So that was the geometric part. So now, so that gives high-level goals for the exploration. It's useful for obtaining global theoretical guarantees on the exploration time. But the analysis assumes that the robots follow the shortest path. Instead, if we allow an extra budget to the robots to add detours, that can improve the map. So what I mean is, like, this is what mutual information basically is. Like, given 2 random variables, let's say the robot and the environment, like if you how can we mutual information in the occupancy. So this is again the occupancy grid representation that we saw earlier. The blue dot here is the robot. It predicts like how future measurements will decrease the robot's uncertainty associated with all the grids. So we have certain uncertainty built into the grids because it is a problem. Like I said, the occupancy grid is probabilistic. Like this, the white person here has a very low probability of it being free, very high probability of it being free, but it has some uncertainty. Same with the black cells here. and the gray cells here. So if you see this image on the right, that shows that this is where mutual information is high. So if the robot goes to the points here, it will obtain more information about the environment rather than just staying where it is. So here mutual information is really low because the robot is already there and can sense its surroundings from that position. Yeah, so the idea is to like once you have this is the start position, S is the start position, T is the goal position. We place a grid over the path, so the robot can sort of increase maximize the information gain of the path, so it can take detour, like visit all these vertices here instead of taking the straight path, so as to decrease the uncertainty in the map. So this is called the ST submodular orienteering problem. So it's what it does is you have a certain budget and you have some reward, and you want to maximize the reward while being within the budget. So you can't just go to all these vertices here, because that will be ideal that you can get the max information, but don't have that much budget. So let's say you double the budget, so it probably can go to this one, go here. So that's the orienteering problem, where you're given a budget and you want to maximize some reward. So that's what we implemented here as well. And as far as so what happens with this is, like, you add a budget and you go back to the comparative ratio here and you add that term here. So let's say the budget is 2, then it becomes 2 times 2 and this whole function, the formula here. So whatever budget you are providing to each robot, that adds that becomes a multiplicative factor in the function here. Yeah, so as far as the system design goes, this is the hardware that we had used for the thesis, for the project. So we have a couple of Pioneer P3DX robots. We had an Intel Nuke computer, which is the onboard computer that you see here. Probably don't, but it's like really tiny here. That's the onboard computer. This is the laser that we use, the Hokuyu 2D laser, and we also had a Kinect, which is basically a depth sensor. Yeah, so that's sort of a high-level overview of the robotics world in general, and some detail about my thesis as well. So yeah, thanks once again. Thanks. Just want to convey my thanks to Arpita Vijaychalvi ma'am, Mangai ma'am, Rajapirian sir, for giving me this opportunity, especially Rajapirian and Arpita Vijaychalvi ma'am, because they gave me a recommendation for my master's. So I would not be where I am right now because without them, and I'm like extremely thankful to them, and I can't express that enough. And yeah, that's it. With that, I'll open it up for questions. Just wanted to say that I can't talk due to company policy. I can't talk about what I work on at Apple, but I'm open to questions regarding any of the slides that you see here. My just general questions about robotics, where to get started, how to get started, what are some good resources, anything. Like, and you can always reach me on my email or my LinkedIn profile. You can free to connect. Please feel free to connect with me on LinkedIn. And yeah, thanks again. Thanks.
Thank you, Aravind, for your valuable presentation about robotics. Even though it's a late night, I think. Late night, but you are giving a good lecture with a lot of simulations and examples, everything. We are very happy, and I hope the participants must get so many ideas regarding robotics. Our principal, Dr. Arpita Vijaychalvi madam, and our vice principal, Dr. S. Sivakumar, are also watching this session. So they also hear your wishes. Thank you, Aravind, for your nice presentation.
Thank you so much, sir. Thank you.
Thank you. Now the mic is open to you, audience. Participants, please ask your questions. You can ask any questions regarding robotics. Kindly use this opportunity. Participants, please. Aravind, in chat box, they are raising some questions.
Okay, so let
Can
me.
you see that?
Okay, so this is a question from Dinesh. He's my classmate from
Yes, yes, yes.
college. So let's see. How do you? So the first question is, how do you identify the exact location of robot using GNSS data? I am not actually sure what GNSS data is. So I think I am not sure what GNSS data is. Probably I can get back to you on that. The second question is, what algorithm is best to find a plane
Oh,
equation? That's
இங்க
just the
வாடா.
second equation is just the equation of the plane. I don't remember the actual like formula to get that. What is the best? Third question is, what is the best way to find distance of two 3D points, either Euclidean or Manhattan? So that's just the L1 or L2 distance. So if, let's say you have x, y, z, the Euclidean distance is just square root of x1 minus x2 squared plus y1 minus y2 squared plus z1 minus z2 squared. So that's the Euclidean distance L1. So that's basically the formula of how to find the distance between 2 points, either or 2 points in space. I hope I answered one question at least. The second one I do not remember, and the first one I do not know what GNSS is. So, thanks Dinesh for the question.
Any more questions? Participants, please. What is autonomous robots? One more question.
So autonomous robots, I suppose, like autonomous robots are any agents that can make decisions by themselves. So without human intervention, they're intelligent enough to make decisions by themselves. So you don't need to control it via a controller or any other commands that you send to the robot. Uh, the the robot can make decisions on by itself, and that's what an autonomous robot is, in my opinion. Um, yeah, and I also see Ponni ma'am and Shanti ma'am also in the chat. Good to see you all as well, ma'am. Okay, Arun, what algorithm is suitable for robotics? Well, it depends on the problem. There's no one algorithm that's suitable for every problem in robotics. So it depends on what the problem is, and you can like find different algorithms that are suited for the problem. Is multi-agent system possible with all? Yes, it is. So there are different ways of deploying multi-agent systems. So the one that the system, like my thesis was a centralized system. So there's one common entity which knows the positions and states of each robot in the environment. But you can have a decentralized system as well, where each robot doesn't know where the other robot is. So there are multiple algorithms. So the one that I just showed you was a centralized algorithm. There's a decentralized algorithm. There are multiple decentralized algorithms as well. So I can send this presentation with links to like those sort of different algorithms that are there. So yeah, it's definitely, yeah, it is possible.
Okay, thank you, Aravind.
Thank
I
you, sir.
request the participants, any to please give me feedback. Feedback, please. Kindly open your mic and give your feedback. We're watching for the past 5 days, so kindly any to give feedback. No one is ready?
Rajapriyan sir.
Yes, ma'am. Yes, ma'am. Okay, ma'am. Our
Good
HOD.
afternoon. Aravind Preshant, nice presentation. Thank you.
Thank you so much, ma'am.
Thank you, Aravind. Shall I continue, sir?
Yes, ma'am. Yes, ma'am.
Education is the best provision for old age. Once again, education is the best provision for old age. Good afternoon to all. On behalf of King's College of Engineering, I want to take this opportunity to congratulate all the members to taking keen part of this program for 5 days webinar alumni series for from 6/7/2020 to 10/7/2020. I am truly thankful to our management and secretary sir, Mr. Dr. R. Rajendran sir for continuous support. My heartfelt thanks to our principal, Dr. J. Arpada Vijay ma'am, for taking more care successfully completion of this alumni series. I am very much thankful to our vice principal sir, Dr. S. Sivakumar sir, for continuous encouragement sir. I am also grateful to congratulate our resource persons and my students, Mr. Yash Sharmila Thakur, Mr. Surendra Ravichandran, Mr. A. R. Adiraja, Miss Vaishnavi Nagapandian, and Mr. P. Aravind Preshant. I really appreciate and all of you enlightened and your knowledge and presence. I would like to congratulate our participants for active participation of this alumni series. I am also appreciate Mr. Sabanayagam, Assistant Professor Mechanical, for continuous support for all our webinar series. Thank you, sir. My heartfelt appreciation to our staff members and students, those who take part of our program and deliver inaugural address and vote of thanks. Thank you all. And also, I extend my thanks to Mr. P. Rajapriyan and Mr. J. Niranjan Samuel for the enormous cooperation of these 5 days alumni series successfully. Finally, I take this opportunity to propose my sincere appreciation to those who have directly and indirectly contributed to this successful alumni series webinar. Finally, you are planning for a year. So rise if you are planning for a decade, plant trees if you are planning for a lifetime, educate people. Thank you all.
Okay, thank you, ma'am. Our HOD ma'am, Mrs. N. Mankere Karasi, give a lot of support for this entire session. Now, our principal ma'am, Dr. G. Arpada Vijay Selvi, also with us for the successful of the program. Thank you, Aravind, on behalf of our principal, HOD, and management. Now, I request our student, Iswari, third year ECE, to deliver vote of thanks. Iswari, please.
Okay, sir. Good afternoon to one and all gathered here. It's my privilege to have been asked to propose a vote of thanks on this occasion. I would like to extend a special thanks to Mr. P. Aravind Preshant. I also wish to express my gratitude to our management, Principal Ma'am, Arpada Vijay Ma'am, Mangai Karasim Ma'am, HOD of ECE department, and other ECE all staff members. I thank all the participants, those who giving support for all the 5 sessions. Thank you, sir.
Thank you, Iswari. I thank all the participants for the patient monitoring for the 5-day session. I thank one and all gathered here, and also Aravind, and a few participants from other countries also, particularly from Oman. Dr. Baladanda Edupani is also watching all the 5 sessions. I thank you, sir. Kindly fill the feedback. Those who have attended more than 3 days will get a series certificate. Other will get session-wise certificate also. I hope be safe in home. Kindly tune with us. Today at 3 p.m. we are having one more session, international webinar. If you please kindly join with that also. Now we conclude the session. Thank you, one and all. You will receive the certificate within 2 days.
Thanks, everyone. Thank you. Thank you for patiently listening to my presentation. Stay safe, everyone.
Okay,
Thanks.
Aravind. Thank you.
Thanks, sir.
Thank you. Have a nice day.